Hello, this is Mrs. Nearing, and this is part 2 of the acid-base 6 homework problems. Okay, so we're talking through these, and we're on problem number 6 now. So we've got a 0.496 gram sample of sodium propanoate, and whenever you see an ionic compound, you want to think about what ions does it split into. And keep an eye out for things that are typically spectator ions. So the sodium is probably insignificant. Really what we're saying is we're adding some of this ion to the solution. Alright, and it's added to a 50 ml sample of 0.265 molar solution of propanoic acid. And assuming that no change in the volume of the solution occurs, calculate each of the following. And we're given a Ka value. Alright, so 6a says define the concentration of the propanoate ion. So where's that coming from? That's coming from this thing right here. So this thing right here is making propanoate ion. And it's asking for concentration, which is molarity. Molarity is moles per liter. So I want to find moles propanoate and divide it by volume, so whatever volume I dissolved it in. So to find moles, I'm going to take my mass of my thing, which I'll write out the formula NaC3H5O2, just to make sure we all realize what we're talking about here. And if I take my mass, divide it by the molar mass, which is 96.0 grams per mole, you will end up with the moles of propanoate, and that ends up being 0.0517 moles. Okay. What is the volume of my solution? Well, they said to add it to a 50 ml sample and assume that adding the solid will not change the volume. So we have to assume after we add the solid it's still 50 mLs. Okay. So I want to convert my milliliters into liters, so I divide it by 1,000, and that gives me 0.050 liters. And when I solve that, I end up with 0.103. So just like the previous problem, in these types of questions, you might see some simple like molarity calculations mixed in there. So you just have to ask yourself, what's the question asking me? What information am I given? Don't overcomplicate things. It might be as straightforward as just converting grams to moles. That might be all the question's asking you for. And then later on, they'll ask you to do something more complicated with it, with acids and bases. So at this point, you're just asked to find molarity. Okay. Now find the concentration of H plus in the solution. So this looks like I'm given a Ka value for an acid. So usually when I'm given a Ka value, I have to consider the equilibrium system. I'm not given any other information about H plus, so I'm going to assume my H plus is coming from the acid. So I'm going to write out my reaction for my acid dissociating. And I'm just going to use the symbol A, just because propanoate looks like a long kind of pain in the butt thing to write out. So I'm just going to write it HA, and I'm going to set up an ice chart. So anytime you have a K value given, that's a hint that it's equilibrium, and so you should write out the equilibrium reaction, write out the K expression, and then look back over the problem and see what you can fill into your ice chart. So it looks like we just calculated something up here. We just calculated the molarity of the propanoate ion. So that's the thing I'm calling A minus down here. Okay, so it looks like we have 0.103 molar A minus. Doesn't mention anything about hydrogen, so we're assuming that's 0. And then HA, if you look back up here, it looks like our HA, our propanoic acid, is 0.265 molar. Alright, so do our normal ice chart thing, and you've got 0.265 minus X, 0.103 plus X, and so if you plug this into your K expression, you've got H is X times 0.103. We're going to assume that Ka is small enough that I can simplify this to say X is insignificant there. 0.265 goes on the bottom, and that is equal to 1.3 times 10 to the negative fifth. Okay, if you go through this and solve for X, you should get 3.5 times 10 to the negative fifth. So I just took my Ka times 0.265 divided by 0.103, so I'm roughly just doubling my Ka value. And notice in this case, X represents the hydrogen ion concentration. So go back and double check the problem. That's all this problem is asking me for. So this is my answer to B, concentration of H plus ions. pH, this is asking us to use this equation, pH equals negative log of H plus. And don't forget, this equation's on your equation sheet. Okay, so don't worry about forgetting it. It's right there on your equation sheet. So if you do this, you should end up with 4.46 being your pH. When you take the negative log of this number right here that we just calculated. All right, so that's number 6. So it's just a molarity problem. Then we plug some things into an ice chart, solve for pH. How did I know to make an ice chart? Well, it gave me a K value. So anytime you see a K value, it's a good hint that you can write a reaction and do an ice chart. All right, so here's another scenario. We've got HCN, which is a weak acid, and NaCN. So remember, anytime you see an ionic compound, ask yourself what ions will it split into when you stick it in water. So when you have sodium cyanide, really what you have are sodium ions and cyanide ions. And we've seen at this point that our sodium ions tend to be spectators, so that's probably not going to be important in this reaction. So we have a volume, we have a molarity, we've got a pH, we've got a Ka value. So there's a couple different ways of solving this. I'm going to say, well, they give me a Ka value, and they're asking for a quantity. So hey, let's set up an ice chart. So let's first write out my reaction. So it's HCN is going to dissociate to make H plus and Cn minus. How do I know to write this out? Well, they gave me a Ka value. So I'm going to look for an equation that shows an acid dissociating, because that's what your Ka represents. Okay, so your Ka is your H plus and your Cn minus divided by your HCN. All right, and I'm going to set up my ice chart, ICE. And what do I know? Well, I know that my Cn minus concentration is 0.50 molar. Doesn't tell me anything about HCN. I think that is the thing that I'm trying to find. But it tells me that my pH is 9.5. And if my pH is 9.5, that means my H plus concentration is going to be 10 to the negative 9.5. So if you plug that, I'll plug that in my calculator real quick, negative 9.5. Whoops, I left off the 9. Negative 9.5 gives me 3.16 times 10 to the negative 10th. Okay, so that is my H plus concentration. So this is 3.16 times 10 to the negative 10th. And this is going to be our X value here. Notice that this is super tiny. Okay. So 0.5 plus 3 times 10 to the negative 10th is just going to still be 0.5, because this is a super small number. And then notice the thing that we don't know is our HCN. So this is a little bit different. In this case, X is our reactant. Okay, so go in and plug this in your Ka expression. I know the value of Ka is 6.2 times 10 to the negative 10th. My H plus concentration is 3.16 times 10 to the negative 10th. My Cn minus concentration is 0.5 molar, and then my HCN concentration is X. So if I go through and solve for X, I'm going to move the X up here and then take this and divide it down here, so you end up with this, 3.16 to the negative 10th. And as I'm writing this out, it will say there are different ways of solving this problem. I'm just going to try and choose the consistent route of always using your equilibrium thing and ice chart to kind of keep it consistent. Okay, so it looks like I'm going to simplify this. There's 10 to the negative 10th on the top and the bottom. That makes my math a little bit easier. So 3.16 times 0.5 divided by 6.2, and your X concentration is 0.25 molar. Okay, so that means I need to have 0.25 molar HCN in order to get this to work. But the problem asked how many moles. Okay, well, I know that molarity is moles per liter, and I know that I want my molarity to be 0.25. So my volume, let's see, is 0.55 liters, right there, 550 mils. So to find my moles, I would take 0.25. Whoa, I lost it. Okay, so to find moles, I would take 0.25 times 0.55 times 0.55. So your answer is 0.14 moles of HCN. So there you go. And again, there's other ways in which you can go about solving this problem. I'm just trying to be consistent and show them all with ice charts. Okay. So number 8, we've got hyperbromous acid. We're given the acid dissociation. We're given the value of Ka. What we're trying to find is number of moles of OBR that would have to be added to make a buffer solution with a certain hydrogen concentration. So again, there's more than one way of doing it. You could use the Henderson-Hasselbalch equation, or you could use an ice chart. And again, for the sake of consistency, I am just going to keep using ice charts. Why? Because you can always use ice charts, so it's kind of a nice fallback if you're not sure what to do, which I think some of us on these were not sure what to do. Then if you're given a K value, write an ice chart. That's what you should do. Okay, and then you can start filling in any information you're given in the problem, and hopefully that'll give you some hints as to what you can do here. So you've got your reaction. You can write a K expression. They give you the value of K. So let's go through the problem and see what other values we are given. Okay, so we're given a volume. We don't include volumes in our ice chart. We're given a molarity. Okay, so molarity would go in our ice chart, 0.160 molar. And we're given another molarity. So whenever we're given the hydrogen concentration, that tells you the concentration at equilibrium. Okay, which means that my change is 5 times 10 to the negative 9th. And notice, I'll write it out once here, but then you see how this is such a small number. 0.16 minus 5 times 10 to the negative 9th is going to be just 0.16 because this is very small. So our change is negligible. Okay, so we know our molarity of HOBr, we know our molarity of H, and the question's asking us about the OBr. That is our unknown. That's the thing we're trying to solve for. Okay, so in here, this is actually going to be our X. And again, change is super small, so I'm going to ignore this change there because it's such a small number. So then you go down here and plug it into your ice chart. Sorry, we just made an ice chart. You're going to plug it into your K expression. All right, so remember K is equal to 2.3 times 10 to the negative 9th. That is given up here in the problem. Your H plus is given. It's 5 times 10 to the negative 9th. Your OBR concentration is unknown. That's our unknown. And then your HOBr is 0.16. Okay, so to solve for X, I'm going to rearrange this. I'm going to take 2.3 times 10 to the negative 9th. And I'm going to multiply by 0.16, and I'm going to divide by 5 times 10 to the negative 9th. Notice how this math works out a little nicely, because my 10 to the negative 9th cancels out, so it's just 2.3 times 0.16 divided by 5 gives you 0.0736 molar. And ask yourself, what is that again? Oh yeah, that is the molarity of OBr minus. But they want to know moles. Okay, so molarity is moles per liter. The molarity is 0.0736. The moles are what we're trying to find. And the volume, okay, here's why they give us that volume. It's 0.125 liters. Okay, so I'm going to take this time, so I'm going to take my 0.0736, I'm going to multiply it by 0.125, and I will get my moles, which is 0.0092 moles. Is that reasonable for sig figs? I have not been paying attention. I think so, yep, because this number has 2 sig figs in it, so my answer should have 2 sig figs. Alright, so there we go with number 8. Okay. Cruising through. Whoops, I missed one. 8. Here's number 10. Whoops, sorry, I missed number 9, it looks like. Okay, well, let's skip to number 10 for now, and then we will figure out number 9 in a minute. Okay, so number 10, you've got a couple of different acids and their K values, and you want to figure out, of these options, which is the best for preparing a buffer with a pH of 7.2. So what we want to do is you want a buffer is best when the pH is close to the pKa. So you can go through and find the pKa, which again is the negative log of the Ka for these things. You'll find the pKa for this first one is 6.38. The pKa here is 7.2. The pKa down here, I'm not even going to figure it out. It's somewhere between like 1 and 2, so that's way off. So we're choosing between these first two options are relatively close. This one here seems to be the best because the pKa is closest to the pH. Okay, so your explanation would just be you want to choose something where the desired pH is close to the pKa of your acid component. So let's say you make this buffer. Okay, let's say you make one that's like, 1 molar of your acid and 1 molar of the base component. And let's say you double both of them. Let's say you make them both 2 molar. What is that going to do to my pH, and what's it going to do to my buffer capacity? Well, my pH is only affected by the ratio of these two things. So your pH will remain unchanged. As long as you keep that ratio consistent, you can make it, 1.5 and 1.5, or whatever the ratio is. As long as it stays consistent, the pH will remain unchanged. And if you're going to think about why, is remember, if the concentration of the acid and the conjugate base are equal, then pH is going to equal the pKa. The other way of thinking about it is this, let's see, pH equals pKa plus log of A minus over HA. So you see that the pH is determined by the ratio of your weak acid, weak base components, not the absolute value. So the pH remain unchanged, but the capacity will increase. So the more concentrated your components are, the better the buffer can withstand change in pH if you try and add some other acid or base to your solution, because you're going to have more buffering components available to react with whatever it is you try and add to it. Okay, so that is problem number 10. And that was the end, but I believe I missed problem 9, right? Okay, let me make sure I didn't. Okay, so let me try and just write problem 9 here on this last page. Okay, so problem 9. Let's go back to that one. What do we know? We've got a 0.35 molar solution of HOCl. And we know that the volume is 550 milliliters. We know that the Ka value is 3.5 times 10 to the negative 8. And we know we want the pH of the solution to be equal to 8. And the question is moles of OCl minus. Actually, the question asks us for moles of KOCl, but KOCl is when you dissolve it in water, it makes OCl minus ions. So, all right, phew. Okay, so I've got a weak acid, I've got a K expression. So again, I am going to write out my acid dissociation reaction and set up a nice chart. And again, there are other options, like you could use Henderson-Hasselbalch, but I'm just trying to be consistent and show you that you could use the same problem-solving strategy no matter whether you're dealing with a pure weak acid, pure weak base, a buffer, or a KP, KC, any of these K problems. You can use the same general setup. Set up a nice chart, solve for the unknown. All right, so identifying what I'm given in the problem. I'm given a molarity of my HOCl, 0.35 molar. I'm not told anything about H+, I'm assuming that's 0. And then OCl minus is the thing I'm trying to find. So it looks like that is going to be my X. Let's see, I'm told that the pH is 8. So the pH tells you the H+ concentration at equivalence. Okay, So your H plus concentration is going to be 10 to the negative 8. 10 to the negative 8. So that means the change was 10 to the negative 8. And this is minus 10 to the negative 8. That's a super small number, so at equilibrium, this is still going to just be 0.35. And same thing with the x. I'm going to go ahead and assume in advance that x is going to be a lot bigger than this number right here. So that change is insignificant. So when I plug it into my k expression, let's see, h is 10 to the negative 8th. OCl minus is my unknown, and then my HOCl is 0.35. And then they told me the value of Ka over here, it was 3.5 times 10 to the negative 8th. So when I solve for x, it's going to be 3.5 times 10 to the negative 8th times 0.35 divided by 10 to the negative 8th. Notice how those cancel out. That's nice. So it's just 3.5 times 0.35. So x equals 1.23 molar. And again, x, what does that equal? That equals my concentration of OCl minus ions. And the problem asked me for moles of OCl minus ions. So I'm going to take my molarity equals moles per liter. And it's 1.23 molarity. My volume was given up here, 550 milliliters, so that's 0.550 liters. So if I solve this, my moles is going to be, whoops, my moles is going to be times 0.55, 0.67 moles. So this is my final answer right here. So make sure you go through and solve the question that the problem is asking you. All right, and that is it. Please feel free to email me if you have more questions.